Okay, so I have a little bit of time here, so I wanted to continue my my CHIP8 emulator, and I was going to implement some more executions on it. So open up Sublime, opens up on the wrong window, of course, and then we also want to. So right now. If I walk through it, not all the instructions are implemented, so we need to go ahead and implement some more on the CPU. So right now we have, I did a little bit before, but I implemented the clear and the return, the jump and the call address, and I have a list of them here, so I'm going to keep going down the list of which ones to implement next. So I see VX byte. This one skips the next instruction if the the address here is equal to this byte. So we're going to look at the next instruction then. So we need to grab the register there. So VX is get register CPU instruction. That's a register. And then we need to do we'll call it compare val. That seems to be fine. Instruction value there. And then what we'll do is if current val at VX is compare val, the interpreter compares VX to the compare val, and if they're equal, it increments the program counter by 2. So they're equal, so what we're going to do is CPU PC increment the program counter. And let me look at increment PC. It automatically does it by 2, so we're okay with that. And we're going to skip the next instruction. Okay, and so then this next one is VX byte. Again, we're going to break there. So it's basically going to actually do the same thing, but we're just going to do the opposite of this. So here we're going to look at it, and then if they're not equal, skip the next instruction. Cool. And then this one is going to be case SEVXVY, which is going to compare two registers to see if we should do it or not. So, and current val at VX is get register CPU instruction dest reg, and then in current val at VY is get register CPU get the two registers at those values, and then if actually I should just be able to do this. This is so much cleaner. I don't know what the fuck I'm doing. So if Vx is equal to Vy, then we're gonna skip the next instruction. I should actually probably go back and refactor these. Make sure we can still compile here. No, what is here? No member increment. Oh, oops, this is not C++. Can't type today. Cool. So that's SE VXVY, and then we're gonna do now the load. So case is load VX byte. The interpreter puts the value of the byte into that register. Oh, it's a load instruction. Slow morning. I'm still drinking my coffee. Okay, so oh no, actually I don't even need it because we're just gonna load it. So int we'll do set register. I honestly forget though. Oh, it takes the CPU and then the destination register, instruction, dest register, and then the val. It can actually be simplified to val. And this can also be val. Okay. Add is next. Add is next. I'm gonna just put them in order here so they're easier to read. That's add. Cool. Load registers. So here we're gonna do case LD VX into VY. Oh, okay. Get register CPU instruction dest register, and then VY is get register CPU, but this time we want the source register, and then yeah, then we're gonna do set register. This one loads VY into VX, so we're gonna do CPU instruction. Actually, I don't even need to get that dest register and then VY. We can actually tighten that one up. It's just two instructions. Case. Here we go. So this is some actual logic here. It ORs these two, and it's going to set it to VX. Performs a bitwise OR on the values of VX and VY. By the way, you're wondering, I have the instruction set here on a piece of paper. So OR performs a bitwise OR on the values of VX and VY, and then stores the result in VX. A bitwise OR, yeah, okay. I'm not going to go over what an OR is, but so we can do VX is get register CPU instruction, and VY cool. So we have Vx and Vy. Now we need to OR them and store them. So I'm just going to call it result. And then we're going to store it in that register. Yeah, I'm just going to store in the register. Something I'm just thinking about is the fact that I've been casting, these are all integers. Let me do get register real fast. Well, unsigned chart, it doesn't really matter because these are all smaller, so it'll just be widened every time. They'll just be 0 extended every time I do anything with the char into an integer. But it looks a little weird now I'm thinking about it. Oh well. We're going to set the register, the CPUs, the instruction is, so it loads it back into the destination register, and we're going to do a result. Let's make sure this still builds, or what did I, oh, oops. Yeah, because we're going to OR 2 registers. Case and Vx, Vy. Same thing pretty much. Actually, I can just kind of copy this. But here it's just going to be an AND. Okay. And then I can actually just copy this again. So we're going to do the XOR. Hardest thing for me to type is the XOR, or 6. It's the hardest key I have to hit anything on here. And then we have adding of 2 registers, because add up here was just an immediate value into this register, and so we want to do 2. We basically want to now do it, but do the same thing for 2 registers. So we're already getting Vx, Vy. Result is Vx plus Vy, and then set register. It's going to set, because we just set it into what Vx is. Sub. Easy enough. Shift right. So shift right on the CHIP8 is a bit weird now, because basically it says shift right. So we set Vx. Well, here let's kind of do it like this. Shift right Vx Vy. We may have a Y here. So the way it works, it's optional. So the way the shift right works on the CHIP8 is the least significant. If the least significant bit of Vx is 1, then the Vf is set to 1. Otherwise, it's 0. Then Vx is divided by 2. But on my instruction set here, it says that the Vy is optional. Same thing with the shift left. The least significant bit of Vx is 1. Then Vf is set to 1. Let's go over here. Here's the Vf1. No, we never tried rebuilding. Good thing we did this. 413. forget that never works on here. Here we go. So let's try a full fresh build. Great. I gotta think about this one for a minute. Okay, so we get Vx, and then what we're gonna do is result is going to be shifting to the right one. Now we need to check if the least, now this is why I'm confused, because if the least significant bit of Vx is 1, then Vf is set to 1, otherwise it's set to 0. So we're just going to set Vx to whatever the least significant bit here is. Oh, and then it says Vx is divided by 2, but shifting right is dividing by, shifting right by 1 is dividing by 2. So what we can do is, okay, so we can actually see, if Vx and the value we want is just whether or not the 1 is set. So is that equal to 1? If it is, we're going to do set register CPU VF. We're going to set the VF flag to 1. Actually, there's a way better way to do this. We could do and 1 here, because we also need to set it to 0 if it's not. Else beyond Vx. Set. Yeah, okay. And then we divide by 2, and then we set it there. Simple enough. But it still doesn't explain what this Vy is, because it looks like it's like this optional thing. Maybe in here it'll actually say something about... because it has enough space for... the instruction itself has enough space for another register. I mean, right now, basically, the first... the upper nibble is basically just what the instruction is, and then the lower 2 are on which register it's for. And right now we're only using this 1, so there's a whole nibble that's not being used. But it's optional here, so I don't really understand what it's for. I thought maybe it'd be like, you know, the amount of times you want to shift, right? So like you could set Vy, the register, to be how many shifts you want. So if you want 4, we could replace this with 4 and set the lowest bit. I'm going to leave it as is, and then if it's a problem, we'll notice it when we're running programs. If things are just crashing or not working, we'll know that it's wrong. So we'll come back to that one. Well, actually, let's first... cool, still compiles. All right. Sub n. I'm not exactly sure what this one is. It says here that Vx is equal to Vy minus Vx. Okay, so easy enough. We can just kind of grab the sub stuff, but we're doing something else too. So we're going to set the destination register to be the subtraction there. not borrow. Set VF equal to not borrow. Vx is subtracted from Vy and the result is stored into Vx. We'll just put a to do here. That's a good enough note for me. I'll know where to look on this thing. By the way, if I actually do this and I want to find the CHIP8, yeah, I'll just do CHIP8 spec. This is what I'm looking at. So I just have a printout right here. Maybe I should just use this. This will probably be better. But here's what I'm looking at, where it's basically saying Vx is equal to Vy minus Vx. Oh, this one's actually Vx minus Vy. This is Vy minus Vx. Vy minus Vx. And then set Vf equal to not of the borrow. Oh. If there's a borrow, then we're going to flip it, whether or not there's a... I'm not sure what this symbol is, though. I'm going to come back to that one, but we can do the shift left. SHL Vx Vy. So shift left again is basically if the most significant digit is 1. This is for the most significant, so most significant bit. This is pushing some of my knowledge here. Right? Yeah. I'm not entirely confident how to actually represent that. Well, let's just get a calculator. We'll set the most significant bit. Actually, let me look at set. Needs to be of a char, and an unsigned char is 8 bits. So whatever the highest of 8 bits is, but what is that as hex? 40. Let's try it. And then here we're going to change the most significant bit on the axis set, and then we're shifting the opposite direction. And then I keep looking back on this thing, but according to this, it says, yeah, they're not equal, or I'm sorry, the Vx is multiplied by 2. Shifting. Cool. Alright, we're done with those, with the instructions that start with 8. That was a lot of them. Let's do the SNE, and then I'm probably going to call it for a day here. Skip the next instruction if Vx doesn't equal Vy. That was a bad idea to jump like that. Oh. I'm jumping around here way too much. Alright. So we'll, this is SNE, and basically it's saying that skip the next instruction if Vx doesn't equal Vy. So if Vx doesn't equal Vy, then we're going to increment the program counter. The values of Vx and Vy are compared. If they're not equal, program counter is increased by 2. Exactly what it is, so we're getting both of them. Cool. And we just want to make sure that, well, let's make sure it still builds. So build doesn't. Oh, I have like a tab in there or something? No, just tons of spaces. Cool. So let's take a look. So get diff CPU-C. We added a good amount of instructions here. Ooh, I have some ugly ones. I can't stand that at the end of these, so clear and do okay, and then get diff CPU. Okay, looks good. One for the OR Vx Vy. Oops. Let's try it again. Yeah. Cool. So, it's really fast. Where do we, the load? So, added, added new execution commands to the CPU. So we added SCVX byte, we added SNEVX byte, we added SCVX VY, LDVX byte. We also added addVX byte, LDVX VY, or VX VY. We also added and VX VY. XOR VX VY. Add VX. Actually, we had that one beforehand. Oh no, I'm sorry. We added the other one. Add VX VY. And we had the VX byte beforehand. Sub VX VY. Shift right. VX VY. Sub N VX VY. And then shift left VX VY. SNE VX VY. Yeah. We will need to revisit sub N VX VY in order to implement the setting of the VF register there was a bar that I'm going to revisit sub nvxvy in order to implement the setting. In order to set the VF register based on whether or not there was a borrow that occurred during the subtraction. Cool. Perfect. All right. Cool. That's it. Thanks a lot. I'll have to make another one and implement the rest of the instruction set.